Hello and welcome to another exciting segment in our thermodynamics series. Today's lecture we'll be talking about exergy, a new concept for many of you. Let's start by determining what exactly exergy is. So what is exergy? Well, exergy is actually a property, another thermodynamic property, one specifically that quantifies how much of a system's total energy can be converted to useful work. So as you know, much of the energy that's being transferred in system does not get transferred to useful work, but the part that does, we're going to call it exergy from this point on. And this is a property that used to be called availability in the old days. So you might have seen it in some texts and in various places under that name before. Exergy, obviously, because the useful work that is done by a system is useful, often what we're looking for, is often related to the economic value of energy. So power plants, those sorts of places are going to be more and more interested in the exergy of the various processes. Unlike energy, however, it is not a property that is conserved. There is no such thing as conservation of exergy. Exergy is destroyed, we say, or reduced by any types of irreversibilities in the system. For example, friction, throttling process, rapid heat transfer are all processes that are going to destroy exergy. So let's define it formally here. Exergy, call it the maximum theoretical work that can be obtained as the system comes to equilibrium with its surrounding environment. We're going to be at a fixed state, which we're going to call the dead state. So let's write that up. Environment, surroundings, we're going to call the dead state. We're going to call it T naught, P naught, etc. The properties of the surroundings. Standard atmosphere would be a typical one. Exergy itself, we're going to denote it as an uppercase E with serif fonts, because we're starting to have a lot of symbols with E's. So let's try and use that symbol here to denote the extensive property exergy. And the value of exergy can be shown. I'm not going to go through a long derivation here. I'm simply going to state how we're actually going to quantify it. It's the change in internal or thermal energy between the system and the state it's in now and the surrounding environment, or the state of the system if it were at the surrounding environment's condition or the dead state's condition, plus P of the environment, the dead state, times the difference between the volume, the total volume of the system minus that of the system if it were at the environment state, minus the temperature of the dead state, times the entropy of our system minus its entropy if it were at the dead state, plus the kinetic energy of the system plus the potential energy of the system. So I encourage you to follow through the derivation of this expression for exergy. It's very, it's rigorously done in Moore and Shapiro. It basically comes off of the TDS is equal to du plus PdV relationship, which you have seen in Thermal 1. Note that the kinetic energy and potential energy terms in the definition of exergy here are with respect to the environment itself. So for example, planet Earth is moving, but the kinetic, and if that's our environment, then the kinetic energy is defined as this relative speed of our system relative to planet Earth. And if we're on a different system that's moving, it would be with respect to that environmental system. Similarly, with the potential energy, we have to define a datum around which we're going to define the exergy. Interestingly, the P naught, V minus V naught term, is to account for the fact that, as a system does work on the surrounding is also doing work on the system. We'll account for that as well. That tends to reduce the amount of exergy that's being produced. Voila, that's the definition of exergy, and we're going to use a little example here to sort of show what we mean by that P naught times V minus V naught term in terms of a piston that's expanding slowly. So let's look at that here. I think it's easiest to see this work that is done by the surrounding on the system by an example such as this one. So I'm just going to draw a simple piston and cylinder system, so a closed system enclosed by a piston and a cylinder that's originally at a state P and V, just like above in the expression that we have there for Exergy. And that system is going to expand, so push on the piston until the volume, or the pressure inside the cylinder reaches the surrounding pressure P naught, and that's going to define the volume inside the system as V naught. So the volume of the system when it's in equilibrium with the surroundings. That's what that means. So there is work being done here. The work is the integral of PdV as we go from state 1, which is the left-hand diagram, to state 2, which is the equilibrium with the surroundings. And you're used to seeing that probably on a PV diagram from thermo 1. It's an expansion of the system, and that's what does work. And usually we denote that work as the area underneath the curve from 1 to 2. And that's not quite accurate entirely, right? Because we're not expanding this piston all the way down to 0. We're really expanding it all the way down to P naught, the pressure of the atmosphere. So all the way down to 0 bit is only correct if we're going to be talking in terms of gauge pressure. But normally when we express in terms of absolute pressure, then we really need to specify that the work available is only the work done between up to P naught, at which point the system is clearly not moving. Okay, so that illustrates that second term underlined there on the definition of Exergy. All right, so now expanding. I should also highlight that we can think of Exergy as the minimum amount of work that's needed to take a system from the dead state to any other state. All right, so just as the Exergy is the maximum amount of useful work that we can get done out of a system when it's in a new state, it also necessarily represents the minimum amount of work that's going to be needed to move it off of the dead state. Minimum because in practice, we're going to have to fight some irreversibility, so we're probably going to have to add in more work than the Exergy value to get it from the dead state to some arbitrary other state, T, V, P, etc. So rewriting or expression for Exergy by expanding for the kinetic energy and the potential energy. That's going to give us an explicit form of E, where we can work to figure out what all the parameters that we need are. Let's write those down. The internal energy or thermal energy difference term with respect to the dead state. I just realized I've forgotten my naught there for P, so that's a P naught right there. It should be there. The TDS, T delta S term, T naught times S minus S naught, plus half mv squared for the kinetic energy, and mgz for the potential energy. So n is with respect to my dead state. Spell that equation 1. In an intensive form, the property Exergy can also be written. We're going to use a lowercase e for that. So pay attention. That's also a symbol that we use for stored energy, specific stored energy. So we're going to have to really work on the context here to know what we're talking about. But that's equal to lowercase, the difference in lowercase u's, plus P naught times delta V, minus T naught times delta S specific, plus half V squared plus GZ. That's going to be your second equation. So let's call that equation 1 and equation 2 for extensive and intensive form of the Exergy respectively. Okay. All right, let's look at an Exergy balance for a closed system. We're going to be using Exergy very often for bookkeeping. So doing an Exergy balance on a closed system as that system goes from one state to another is going to be one of the ways that we're going to be using this. In this lecture here, we'll talk about measuring the rate of Exergy change and we're going to associate that with irreversibilities as well. But for now, baby step, let's just stay in the extensive property and intensive property form and look at the change in exergy between two states for a closed system. So in the simplest form, if we know both of the end states of the system at which we're interested in doing this exergy balance, as well as the environmental dead state, the system and the dead state, then at that point, then the change in exergy that occurs from one state to the other, on to state 2 say, is simply going to be the difference in the exergy between those two states, which we can quantify using the equations that we've got above, specifically the extensive form of exergy, equation 1. Then we can compare all the different types of energies that form the exergy between those two states, and you'll notice that the dead state falls off in a lot of these terms. Like, for example, in the first term here on the right hand side of the equation, the internal energy, the dead state cancels out between state 2 and state 1. Similarly, for the work done on the system by the surroundings, the dead state falls off as well. We're just left with the P0 term, don't forget that. The TDS term, same thing. And the kinetic and potential energy terms include both and states only. So not path dependent, clearly, just the end states matter in this particular case. Preparing you for what's about to come next here, that will not be the case, the path independence bit, once we start to include the irreversibilities of the system. We could write a similar expression, by the way, which I'm not going to rewrite here, for the intensive form of exergy, lowercase. Again, don't confuse it with stored energy. It's exergy, specific exergy, not specific energy. All right. Okay. So as I mentioned earlier, in practice, exergy is often lost during a process. And you're familiar with that. Every time you look at a process that includes friction, that energy that's being expended to fight this friction is effectively lost energy, and therefore lost exergy, energy that's no longer available for doing useful work. So all kinds of irreversibilities are going to participate in that: friction, throttling, all these types of reversible process. Rapid heat transfer being another one. So another way to calculate exergy is to look at the processes directly, not just the end states, but the process that takes us from state 1 to state 2. And so that's going to bring about the irreversibility effect that's happening while we're doing that. So let's look at some process between state 1 and state 2. So exergy is going to be exergy difference, Again, it's going to be as before in equation 3. Exergy at 2 minus exergy at 1, which equals what's expressed by equation 3. But it's also equal to exergy that's being transferred into the system as a result of heat transfer in. So this is going to give us more energy to do useful work, right? It's going to be reduced by whatever exergy was transferred out or expended to produce a useful work already between 1 and 2. That might be a reason why we expend exergy, right? After all, that's the whole point. But it's also going to be reduced by whatever process we've used between 2 and 1, which is going to destroy some exergy. So the exergy destroyed during the process from 1 to 2 may include some irreversibility, and that's going to diminish the amount of useful work that the system can do. So we're going to express that as the exergy transferred in due to and that's E sub Qin. The exergy transfer due to workout as E subscript workout. And the new bit here, the exergy destroyed, is sub D, big E, equation 4. I'm also not going to go through derivation for each of those terms, but you can show, and the Moore and Shapiro book does that as part of your reading for this module, that the exergy transferred in due to heat transfer is equal to the integral of 1 minus the dead state temperature divided by the boundary temperature at which heat transfer takes place times the increment in heat transfer that happens while the system is at that particular state on the way to state 2. So it's an increment. TB could change as a result of that, and so you're going to slowly integrate this path from 1 to 2. So TB is the temperature of the boundary where the heat transfer occurs, and dQ is the heat into the system during that part of the process. Notice that term in parenthesis, 1 minus T naught over TB, very much like a Carnot efficiency, doesn't it? Where T naught would be your cold reservoir and TB would be your hot reservoir. And so it kind of makes sense that if you take this Carnot efficiency and you multiply it by an amount of heat transferred as a result of that process, that would give you the maximum amount of work that could possibly be produced by this particular step. And that's what we've got here. So we're adding all this maximum work that can be produced during the process as we go from state 1 to state 2. That's what that term means. Now for the work out term between 1 and 2, then that's not very mysterious. It's simply going to be the total workout done between 1 and 2 minus the work done by the surroundings between state 2 and state 1, just like we showed before. So that's our second term on that equation. Last but not least is this Exergy Destruction term, that new term for us. And that's going to be one that we're going to spend a little bit of time talking about. Extracted from the system is no longer available, and so therefore the Exergy 2 is used by that amount as well. So this Exergy Destruction term, E sub D, equal to the dead state temperature times this new parameter sigma. And so sigma is path dependence between 1 and 2. And that represents the irreversibilities of the systems, or the amount of entropy that's being produced as we go from 1 to 2 as a result of those irreversibilities. So we're going to call that sigma the entropy production term. Sigma is entropy production term. Most of the time we're going to be interested in the entropy production rate of a process. So we're going to call that sigma dot. And we're going to just end our short lecture on Exergy here on that note by recasting this expression 4 for the difference in Exergy, on a rate basis. It's often more practical to express the change Exergy on a rate basis. Express the change on a rate basis. So I'm not changing anything here. I'm just going to take the derivative of both sides of equation 4 above. Okay, recall that equation 4 is the expression that takes into account the process that takes us from state 1 to state 2. So that's going to mean on the left-hand side that we're looking at the derivative of Exergy with respect to time during that process. And that's going to be equal to the sum, another way to look at the integral, if you will, the sum over however many intervals I'm interested in, of 1 minus the dead state temperature divided by the temperature of that particular interval times the rate of heat transfer during that same interval. We're going to call that E dot sub Qin. And it's going to be that's the sum of all these different intervals. We're going to subtract the work that was extracted from the system, the rate of which work was extracted out of the system. So power, if you will, the useful power coming out of there. We're going to call that E dot workout. And finally, we're going to subtract the entropy production term, which is going to be T naught times sigma dot over that part. So that's going to be E dot D. So that's the entropy production term. That's the effect of irreversibility on the process between 1 and 2. And voila, that's it for Exergy for this week. Go ahead.